So here we got a nice polynomial problem. We are given a polynomial which is defined as x minus a1, x minus a2, so on up to x minus an minus 1, where a1, a2, and an are the distinct integers, and we have to prove that polynomial p of x cannot be written in form of the product of two non-constant polynomial with integer coefficients. So for proving this, for solving this problem, I'm going to use the method of contradiction. So let p of x can be written in form of the product of two non-constant polynomial. So this simply implies p of x equals g of x minus h of x, where g and h are the polynomial, non-constant polynomial with integer coefficient. And now we know that p of x equals x minus a1, x minus a2 up to x minus an minus 1. So we can simply substitute the value and we'll obtain x minus a1, x minus a2 up to x minus an minus 1 equals g of x into h of x. And now we can simply say that p has degree n. So the maximum degree of any one of g and h is n minus 1, because any one of them cannot be constant. We already have assumed these all are the non-constant polynomials, so the maximum degree of any one of them is n minus 1. So I'm going to let that degree of g of x is n minus 1 and the h of x is linear. So this is an important assumption. We know two things here, that a1, a2 up to an are the distinct integers and g and h are integer polynomial. We know these two things. So we can simply say that g of ai and multiplied by h of ai is equals minus 1, where I is 1 to n. And here can be the two cases. Case 1 is g of ai is 1 and h of ai is minus 1. And the case 2 is g of ai is minus 1 and h of ai is 1. Except these two cases, nothing else is possible, because we know that g and h are integer polynomial and the input a1 to an are also integers. And now this simply implies that g of ai plus h of ai would be equal to 0, where I is from 1 to n. And now next thing is maximum degree of above expression is n minus 1, but the number of roots are n. We can clearly see the number of roots which satisfy above expression is n. So we can say that g of x plus h of x equals 0 for every x belongs to real. So this is a concept of infinite root. We know that if polynomial has degree n and the number of roots is n plus 1, so it simply means that polynomial has infinitely many roots. So this simply implies that g of x plus h of x equals 0 for every x belongs to R. So now we can simply obtain that g of x equals minus of hx, and we can substitute this value and we'll obtain p of x equals minus g of x square. And here the thing that contradicts our assumption, that left hand side of this expression has a positive leading coefficient, because we know that p of x has the positive leading coefficient, but in the right side of the equation has a negative leading coefficient. So this simply contradicts the fact that we already have assumed that p of x can be written in form of g of x into h of x. So this is the point where our assumption contradicts, and this is the place to stop.